It is the 4th of August 1940 and the sun is setting over the Kentish coast near Dover. A young radar operator sits in a concrete bunker, his eyes fixed upon a cathode ray tube that glows with an eerie green phosphorescence. On the curved screen, blips of light begin to appear, moving slowly southward across the display like luminous creatures swimming through an invisible sea. There are dozens of them. Perhaps 100 aircraft are crossing the channel right now, flying in tight formation towards London. But this operator cannot see them. No one in the bunker can see them. Yet every person here knows exactly where they are, how fast they travel, and when they will arrive. The operator reaches for the telephone handset. Within moments, the information flows outward to fighter squadrons scattered across southern England. Hawker Hurricanes and Supermarine Spitfires scramble from their airfields, climbing towards the descending Luftwaffe bombers with the precision of a chess player who somehow knows his opponent's moves 3 steps in advance. The Germans have no idea what is happening. They have no conception that the British have developed a technology that allows them to see in the dark, to perceive the invisible, to know things that ought to be unknowable. To the Japanese, who would later hear whispered accounts of this capability, it seemed like pure sorcery. It was neither magic nor miracle. It was radar, and in the summer of 1940 it would save Britain from invasion. Before radar existed, air defense was a desperate gamble. Fighter pilots relied upon their eyes, scanning the sky from the moment they scrambled until they spotted enemy aircraft in the distance. It was a system that had worked adequately during the First World War, when speeds were low and altitudes modest. But by 1940, German bombers could cruise at 350 kilometers per hour, traveling at altitudes where they were invisible to ground observers on a cloudy day. A Luftwaffe formation could appear over London with barely minutes of warning. British pilots were scrambled endlessly, flying hundreds of sorties, burning vast quantities of precious fuel in the hunt for enemy aircraft they might never find. The losses were staggering. In the month before radar became operational, the Royal Air Force was losing more pilots and machines than German aircraft were destroying. The mathematics were catastrophic. If this trend continued, Britain would have no fighters left within months. The Air Ministry knew that some new technology was essential, but no one could quite articulate what it might be. How could anyone possibly detect an aircraft that was 10 kilometers away, beyond the horizon, invisible against the clouds? The very proposition seemed absurd. Yet there was a theoretical possibility that had been discussed in the scientific literature for years. Electromagnetic waves could be bounced off metal objects. Perhaps, some researchers wondered, these waves might detect distant aircraft before they reached Britain. The only problem was that no one had ever built such a system. The technological obstacles appeared insurmountable. The equipment would need to be extraordinarily sensitive, capable of detecting the faintest reflections of radio waves bouncing back from an aircraft dozens of kilometers away. It would require oscillators of unprecedented stability. It would need amplifiers that could boost weak signals without introducing intolerable distortion. It would need operators trained to interpret displays that did not yet exist. And all of this would need to be operational before the Luftwaffe returned for the autumn bombing campaign. Britain did not have the luxury of time. The survival of the nation depended on solving the impossible. In the winter of 1935, a young physicist named Robert Watson Watt stood in a laboratory at Bawdsey Manor on the Suffolk coast and conducted an experiment that would change warfare forever. Watson Watt was not working alone. Around him was a small team of scientists and engineers recruited from universities, research institutes, and the fringes of British industry. They understood that they were racing against history. Watson Watt's crucial insight was that the problem might be simpler than everyone imagined. Instead of trying to detect the aircraft itself, they could detect the radio waves that bounced off it. They took a simple transmitter, the sort of device that had been available for years, and pointed it towards the sky. When an aircraft passed nearby, the radio waves would reflect off its metal fuselage and return to a receiver. By comparing the time delay between the transmitted pulse and the returning echo, they could calculate the distance. By rotating the transmitter and measuring the signal strength, they could determine the direction. The system was crude, the display was primitive, but it worked. Within weeks, Watson Watt had assembled the first working prototype. It was a Hertzian oscillator, a cathode ray tube receiver, and a telephone handset. The entire apparatus could fit into a single van. Yet this primitive contraption could detect an aircraft at a distance of over 40 kilometers. The scientists at Bawdsey Manor understood immediately that they had invented something that would reshape the conduct of warfare. The Air Ministry authorized rapid expansion. Between 1936 and 1940, a chain of radar stations was constructed around the British coast. They were called chain home stations, and they were unlike anything ever built before. Each station consisted of a tall lattice transmitting tower made of steel, reaching nearly 100 meters into the air, and separate receiver towers constructed of wood. The transmitting stations operated on frequencies around 25 megahertz, generating pulses of enormous power. The receiving equipment was housed in concrete bunkers, shielded from electromagnetic interference. The entire network was connected by telephone cables to a central filter room, where data from multiple stations could be collated and interpreted. A typical chain home station could detect bombers at ranges up to 180 kilometers, and fighters at ranges exceeding 100 kilometers. The resolution was crude by modern standards, but for 1940 it was miraculous. The operators, mostly young women conscripted for war service, could distinguish between formations of aircraft and estimate their size and altitude. The electronics were cutting edge. The cathode ray tubes were manufactured in Britain using vacuum tubes developed by the Post Office and the Telephone Manufacturing Company. The oscillators were built from components scavenged from every available source. The amplifiers operated at frequencies that required new circuit designs developed in laboratories across Cambridge, Oxford, and the Royal Aircraft Establishment at Farnborough. The entire system was so novel that no one knew whether it would work under combat conditions. In fact, for much of 1940, officers in the Air Ministry remained skeptical. Some believed that radar would be unreliable under combat stress. Others worried that enemy bombers might jam the signals. A few senior commanders trapped in the tactical thinking of the previous war doubted whether any technology could significantly improve air defense. These doubters would soon be proven catastrophically wrong. The first operational test came on November 7, 1940, during what would later be called the Battle of Britain. A Luftwaffe raid was detected approaching the British coast, identified by the chain home network, and reported to the command post at Uxbridge. Fighters were scrambled and guided towards the enemy formation using radar information passed by radio. For the first time in the history of warfare, pilots knew where to fly before they could see their enemies. For the first time, a defending nation could concentrate its limited fighter resources exactly where they were needed, rather than scattering them across the sky in desperate searches. The results were immediate and startling. The Luftwaffe suffered a catastrophic loss rate. In a single day, they lost more aircraft than they had anticipated losing in an entire week. German pilots reported flying into formations of British fighters that seemed to materialize from nowhere. They reported that the British knew the exact positions of their aircraft before crossing the coast. They reported a form of detection so uncanny that some whispered it might be extraterrestrial in origin. The German High Command was baffled. They had no radar of their own, and their attempts to understand how the British could achieve such accuracy were failures. When they finally captured a radar station on the French coast and examined the equipment, they were so confused by the technology that they concluded it must be too fragile for practical use. This was a catastrophic misreading of British engineering. The chain home system was robust, reliable, and nearly impossible to jam. By the time the Germans understood what they were facing, the Battle of Britain had been decided. Throughout the rest of the 1940s, radar gave the British an advantage so profound that German pilots began referring to it with superstitious dread. If you are finding this interesting, a quick subscribe helps more than you know. It truly does make a difference. The Japanese, observing from afar, heard rumours of this mysterious British technology and struggled to comprehend it. Japanese naval intelligence received fragments of information from German sources, but the accounts seemed fantastical. The British could somehow see aircraft beyond the horizon? Impossible. It contradicted every principle of physics that Japanese engineers understood. Japanese radar development had begun in 1938, but progress had been painfully slow. Japanese technology was superb in many domains, but the scientific culture that produced excellence in mechanical engineering and industrial design had not yet developed the theoretical foundations necessary for advanced electronics. When Japanese officers encountered descriptions of chain home, they often dismissed them as either gross exaggeration or deliberate deception. Some Japanese pilots believed that the British had recruited technicians from the United States or had stolen designs from German sources. The idea that British scientists could independently develop a technology so far in advance of anything Japan possessed was emotionally unbearable. It contradicted the Japanese narrative of Asian technological superiority. Yet the evidence accumulated steadily. Japanese pilots who had trained on the continent returned with accounts of British fighters appearing from cloud cover with uncanny precision. Japanese naval attachés in Stockholm received reports from neutral sources describing towering antenna structures constructed along the British coast. Japanese intelligence officers noted that the British seemed to concentrate their fighters with impossible efficiency, always arriving at the exact moment and location where they were needed most. By 1942, Japanese engineers finally began to comprehend that they were not facing magic, but a form of technology they had failed to develop. It was a bitter realization. Japanese radar development accelerated frantically, but the Japanese were always 2 or 3 years behind the British curve. When the Japanese finally deployed radar systems on aircraft and warships, the British had already moved to higher frequencies, shorter wavelengths, and more sophisticated detection methods. The technological gap never closed. The American radar systems developed in parallel with the British chain were in some respects more sophisticated. American engineers working at MIT and other laboratories had developed radar technology that was both more compact and more mobile than chain home. American radar sets could be installed on ships and aircraft, whereas the British system was, by necessity, land-based. American centimetric radar, operating at frequencies around 3,000 MHz, could achieve far greater resolution than British systems operating at longer wavelengths. When American forces entered the war in December 1941, they benefited enormously from British experience. The scientific liaison between Britain and the United States, facilitated by scientific exchange missions and direct correspondence, meant that American engineers could learn from the British mistakes and accomplishments. However, the British chain had the advantage of being first. The British had solved the problem when no one else believed it was solvable. The British had operated under the most extreme time pressure, with invasion a genuine possibility and the nation's survival in the balance. British scientists and engineers had built a system that worked, that was reliable, and that provided an unambiguous tactical advantage at the moment when it was most desperately needed. The Americans, arriving later to the problem, had the advantage of time and resources, but they were building upon foundations laid in Britain. The actual impact of radar upon the outcome of the Second World War remains subject to historical debate. Some historians argue that radar was the decisive factor in defeating the Luftwaffe. Without chain home, they contend, the Luftwaffe would have succeeded in achieving air superiority over southern England, permitting the German invasion to proceed. Others argue that the Luftwaffe was never capable of defeating the Royal Air Force regardless of the detection technology available, because German industrial capacity was simply insufficient to replace losses. The truth almost certainly lies between these extremes. Radar did not win the Battle of Britain single-handedly, but it transformed the tactical situation in ways that made victory possible. Without radar, the Royal Air Force would have lost more pilots and aircraft. The margins of victory would have been narrower. The risk of German air superiority at some point during the summer and autumn of 1940 would have been substantially greater. As the war progressed, radar became increasingly integrated into air defense systems. Ground-based radar guided anti-aircraft guns, ship-based radar guided naval gunnery, aircraft-based radar guided night fighters towards enemy bombers. Each application required different engineering solutions, but all were built upon the theoretical foundations developed at Bawdsey Manor. The psychological impact of radar was perhaps as significant as its material effects. Allied pilots learned that they could achieve air superiority through technological innovation rather than superior numbers or training. Axis pilots grew increasingly demoralized as they discovered that their enemies possessed capabilities that seemed incomprehensible. German pilots found themselves under attack from aircraft they had not seen until the last moment. Japanese pilots experienced similar shock when they encountered American aircraft equipped with radar. The knowledge that your enemy possesses a capability you cannot perceive is profoundly demoralizing. In the years after 1945, radar evolved rapidly. The frequencies became shorter, the resolutions finer, the equipment more portable and more reliable. Radar was incorporated into every branch of the armed forces. It became essential for air traffic control. It revolutionized weather forecasting. Today, radar is so ubiquitous that most people do not think of it as a technology at all. It is simply assumed to exist. Few people realize that this invisible network of signals filling the air around us, the technology that guides aircraft across oceans and detects severe weather before it strikes, the system that saves lives every single day, originated in a concrete bunker on the Suffolk coast in 1940, when a small group of British scientists and engineers built a machine that could see in the dark. At Bawdsey Manor today, a museum preserves one of the original chain-home receiver huts. Inside, the equipment has been restored to working order. Visitors can watch the cathode ray tubes display the positions of aircraft flying overhead. They can hear the crackling of the radio waves bouncing through the electromagnetic spectrum. They can stand in the very bunker where operators once sat in the darkness, interpreting the glowing symbols on the screen, making split-second decisions that determined the fates of nations. The experience is profoundly moving. The equipment is crude by modern standards, yet its elegance is evident. The design solves a seemingly impossible problem with materials that were available in 1940, using principles that were so new that most scientists in other nations refused to believe they would work. On the 4th of August 1940, as the sun set over the Kentish coast, the operator in the Dover bunker watched the blips on his screen and reached for the telephone. His hands were steady. His voice was calm. He had no idea that he was participating in a moment of profound historical significance. He did not know that the information he was relaying would save the lives of thousands of pilots and millions of civilians. He did not know that he was wielding a weapon so novel and so effective that foreign observers would struggle for years to comprehend it. He knew only that bombers were coming, that fighters were rising to meet them, and that his job was to guide them together in the darkness. That simple task, performed by thousands of operators across hundreds of radar stations over the course of 4 crucial years, created the technological foundation upon which the modern world has been built. Radar was not magic. It was something far more powerful. It was the application of pure science to the problems of war, the transformation of theoretical physics into practical weapons, the demonstration that intellect and ingenuity could overcome any obstacle that nature or history placed in the way. The Japanese had thought it was black magic. They were wrong. It was something far more potent. It was British engineering, applied at the moment when it mattered most, by people who understood that their nation's survival depended upon seeing what no one else could see. That insight, that determination, and that technological achievement changed the course of human history. And it all began with a glowing green screen in a bunker on the coast of England, where a young operator watched the invisible sky and saw the future approaching.